All right, so welcome to week 2 of Math 202. So we are now 1/12 of the way down. That's a good old, what's that, 6.333% or something like that. So I will take it. But who's counting, right? Anyway, so in terms of homework, I know there are already a couple of questions from section 3.2. So I will share my screen and we'll go take a look at those and see how this goes, and then we'll sort of progress from there. So the questions that people want to see are numbers 7, 12, and 15. So here comes my screen. All right, so here's number 7. So yours is going to at least look similar. So this one says find the second derivative of the vector value function. So that just means we're going to differentiate twice. And so what we should get here is just the derivative, the second derivative of each of these component functions.
Yeah, Bruce,
So
can I chime in?
Yeah, go for it.
So basically, I got my second derivatives for this, and they are, to my knowledge, 100% accurate. I just don't know. I think my issue might be inputting the answer. So I don't know what format it wants the answer.
Okay, well, let's see if we can figure it out. I'm going to try using the kind of notation that I use. So the second derivative of this one would be a -4 sine. So -4 sine of t. And then the second one is going to be a -4 cosine. All right, so I'm going to try it this way. Well, actually, it won't let me. It's even telling me that there's a syntax error. And I see people are throwing stuff up in the chat, so let me actually go look at that. But I'm sharing my screen.
I see people are saying to just use I and J.
Okay.
Yeah, no vector. Just put I plus J.
Sweet. Okay, I got it. Thanks, guys. Thanks, Bruce.
Okay, so like that. Beauty.
Yeah, I'm all set. Thank you.
And my recommendation when you run into that kind of thing again, because it will happen, right? At some point you'll run into something that's got funky notation. Use either what's in the box, like when you hover over. Let me go pull up number 12 here. Show you what I mean. Oh, we actually already talked about number 12. Let's try a similar question. So when you click on the box, it tells you a lot, right? Like this one saying, enter an integer or a decimal number. It will also give you other things, like notice how it says DNE for does not exist, the 00 for infinity, and so on and so forth. So a lot of times it will tell you what kind of format you need. So use that. Or if it ends up being an issue, like you entered it like I would have entered it with those greater than or less thans, but really they're the ends of vectors, and it's not liking you, just send me a message and I will look into it, and if what you did was correct, I will give you the credit because I can manually give you points. Okay, so let's look at number 12. We've already talked about this one before, so let's just kind of real quick recap. So we want to find a positive t when this vector is perpendicular to r prime. So we want to find r prime, and then what do you do with them to determine if they are perpendicular?
Dot them.
Yeah, you dot them. And what has to be true about the dot product for them to be perpendicular?
0.
It's got to equal 0. So you take that dot product, you set it equals 0, and you solve for t. And when we did this before, we found out that there were like 3 different t values, but only one of them was positive. So watch out for that as well. Make sure you're putting in the correct one. So I don't remember who asked me about this one, but if you go back and you look at the video, I think on Friday's video, we talked about this very early on. So I'll have you go reference that. All right, so then let's look at number 15. All right, so this one says we want to find the unit tangent vector to the curve defined by this at a given t value. All right, so let's just start with, how do you find big T? How do you find the unit tangent vector?
T equals r prime of t over, isn't it is the square root of r prime of t squared?
So r prime of t dotted with r prime of t, not r of t squared, because that notation doesn't really make sense anymore. But
Yeah.
yes, you can dot it, take the square root, or just realize it's the magnitude of that vector.
Yeah, the magnitude. I couldn't remember what it was. It's the
all good.
magnitude.
Okay, so let me stop sharing this and let me share the whiteboard. Okay, so do you guys see the whiteboard?
Yeah.
Yeah, okay. All right, so here was R. We had R was equal to 5 cosine. Was it 5, 5? Shit. Hold on a second. Let me go back and find that again. It's 5 cosine, 5 sine. All right. Now someone's going to watch that video, see me swear, and be all offended and never go to my YouTube channel again. And I'm going to be so sad. All right, so 5 cosine, 5 sine, and then 3 sine squared. All right, so let's get r prime. So minus 5 sine, positive 5 cosine, and then this is going to be 6 sine times cosine. So that one's coming from the chain rule. Right, sine squared, the 2 comes out front as a multiple, and then we have to multiply by the derivative of sine. All right, so far so good? So now we need to get the magnitude of this. So that's going to be the square root of 25 sine squared plus 25 cosine squared plus 36 sine squared cosine squared. These first two add up to 25. And unfortunately, these sine squared and cosine squared are being multiplied together, not added together. So we're kind of stuck with them where they are. Okay, but now we're going to divide r prime by these. So we get t, it's equal to minus 5 sine t over all that square root garbage. Ah, whoa, what was that? That was one too many root beers. Let's try that again. Okay, so there's that piece. then this one, and so on. But now we've got that unit tangent vector, and this is good everywhere. All you got to do is tell me what t value to put in. I'll put it in and we'll get it. All right, now they did give us a t value, right? They said specifically, let's look at t equaling, I think for mine was 3 pi over 4. So now let's plug in 3 pi over 4. So this is where we're going to have to kind of remember our trig. I'm going to run it up here. So sine of 3 pi over 4 is root 2 over 2. So we're going to get minus 5 root 2. And then sine and cosine of 3 pi over 4, one's a root 2 over 2. The other's a negative root 2 over 2. But those both become positive when squared. So it becomes a half times a half, which is a fourth, times 36 is 9, plus 25 is 34. So I believe this is the square root of 34. So then for the second one, cosine of 3 pi over 4 is also negative. So we'll get negative, it should have been 5 root 2 over 2. So we're going to get negative 5 root 2 over 2. But again, that's square root of 34. And then the last one, we get root 2 over 2 times minus root 2 over 2. So that's a minus 1/2 times 6 is minus 3. So I'm pretty sure, not confident whatsoever, that this is our unit tangent vector at that point. But notice that the process is like, it's really systematic. You find r prime, you find the magnitude of r prime, and then you divide that into r prime. And it really just depends what these functions are on how gnarly it gets. But I want to show you kind of a faster way. But before I do that, we okay with what I just did, ish? All right, so hearing no questions or anything, I'm going to assume that we're good. Okay, so let me just show you a little bit of a time saver. Let me erase some stuff here. What I'm going to do is I'm going to actually erase all this stuff down at the bottom. And in fact, I'm even going to delete that magnitude of r prime. Okay, so we want to find t. And as always, you got to go ahead and start by finding your r prime. So we did that. But now what I'm going to do is I'm actually going to plug in my 3 pi over 4 here. So I get minus 5 root 2 over 2, minus 5 root 2 over 2. And then this one ends up being 3 minus 3. So this is the derivative vector at this point, which means this vector is pointing in the direction of big T. We just have to normalize it. So now I'll find my magnitude of r prime. So that's going to be the square root of 25 halves plus 25 halves plus 9. So let's see, 50 plus 1868. Oh, well, 50 halves is 25, plus 9 is 34. Hey, check it out. The magnitude of r prime is 34 at this point. And if you kind of I've erased it. It was down over here, but you can still see its remnants up above. And so there was its square root of 34. So now I can just jump right in and do this division. So I get minus 5 root 2 over 2 times the square root of 34, minus 5 root 2 over 2 root 34, minus 3 over square root of 34. And that just dawned on me, I made a mistake up here. There was no 2. But if you look at that and compare it to what we found before, they are identical. But I find this a lot faster when it comes to finding the magnitude. Because think about what we had to do before. We had to try to simplify it with, the trig identities and all that, and then we had to plug it into a whole bunch of different trig values. And this is a little bit quicker, but you can only do that if you're going to be looking at a specific point, and make sure that you don't plug in until after you take the derivative. Because if I had started by plugging it in to the original function, the derivative would have turned into 0, and then we've got problems.
And this only works if we're given a t value initially, right?
Correct. If you weren't given a t value, then you would have had to leave it as that big, ugly expression of t, right? The one that had like minus 5 sine t over the square root of 25 plus whatever else that stuff was. All right, other questions on this one? Cool. Well, hopefully that makes a little bit more sense. Really with t, with big T or big N, right, the normal vector, it's just tedious. Like, it's not hard. It really isn't, because the process is easy. Derivative divided by magnitude, right? And N was the same way, except we're differentiating big T instead of R, right? But again, it's derivative divided by magnitude. Derivative divided by magnitude. It's a recipe. There's nothing to think about. And it's just going to get complicated when the derivatives get complicated. So, all right, so is that good for homework? We ready to kind of move on a little bit? All righty. So what I'm going to do is I'm going to turn off this screen and head over to the whiteboard. All right. So just to kind of refresh your memory where we were last time, we've now kind of nailed vector valued functions. Like we've learned everything we need to know about them in terms of doing operations. And we've seen that it's exactly the same as what we did before. It's just lots of times now, right? We have to do it for each of the components, X, Y, and Z. So good news is nothing new. Bad news is lots of what we used to do, right? And we even started talking about drawing the graphs, and we saw that the graphs, really what we're doing is we're keeping track of where the ends of these vectors are, but they really behave like parametrics, and they're just now three-dimensional, but we define these two new vectors, the unit tangent vector and the principal unit normal vector. And let me just write this down for you again. If we've got a vector R, then the unit tangent vector, which we call T, big T, it's found by taking R prime and dividing by the magnitude of R prime. So that's what we just did on the homework. And then there's also the principal unit normal vector. And I know you haven't run into any homework problems with this yet. for those of you who know me, it's not surprising that I'm doing things in a slightly different order than the book. For those of you who are new to me, I do things my own way, which sometimes doesn't follow the book. But you'll see this guy, the principal unit normal vector, but we found it exactly the same way, except we're taking the unit tangent vector and finding its derivative and dividing by its magnitude. But what we know about both of these is that they're both magnitude 1. That's what unit means. This first one is tangent to the curve, but it points in the direction of travel. So if we think about those vectors, they're moving, right? The vectors are changing as we go. If you follow how those vectors are moving, then that's where this one points. And do you guys remember where big N pointed?
To the center of the curve?
Yeah. So this points to the inside of the curve. So imagine that there's like a best fit circle, let's say, then big N is pointing towards the center of that circle. And so I gave you a little bit of a justification for why this might be useful from the physics standpoint in terms of tangential and centripetal accelerations. But there are all kinds of problems, all kinds of ideas where we want to know which direction we're traveling. And that's where big T is going to come in really useful. And then a lot of times we want to know how the function is curving, and that's what big N will tell us, right? So that's where we got last time. I don't really want to slug out another example of these because they are long and boring and blah, right? So we're going to move on. We're going to keep kind of talking about space curves and all that. And the next topic of a conversation is going to be curvature. So curvature is exactly what it sounds like. It's a measure of, you're going to like how I write this. It's the measure of how curvy the curve is. So I kind of chuckled as that entered my brain, and I was like, oh yeah, that's what I'm going to tell them, because it sounds kind of funny. But I also know that every single one of you know exactly what I mean by this, right? So give me a curve that's not curvy. What would it look like?
Y equals X.
Okay, so a line, right? That's perfect. A line is not curvy. So it actually has a curvature of 0. What? Right? So then as we get more curvy, tighter curves, the curvature goes up. So again, because we live, well, maybe not everyone watching this, but most of us live where we live. We live up in the mountains and we drive mountain roads, right? So think about when you're driving Highway 50 to get down to Sacramento, that road changes curvature all the time. Where it has greatest curvature, those are the places you have to slow down the most because it's a nice tight turn. Small curvature are where you don't really have to slow down because you're just kind of meandering a little bit, okay? So it's a measure of how curvy the curve is. Let me draw a picture of a curve, and we'll talk about places where it's more curvy than others. All right, so here's an example of a curve. Now, there are some places where it has really small curvature. So places like in here have a small k. By the way, curvature we use the letter k for. Yeah, curvature starts with k. We just use C, we use for everything. So that's kind of small curvature there. Here's another spot where it's got small curvature. There's pretty small curvature around there. Now, a location of large curvature is in here. That's a nice tight turn. All right, so there's going to be big K when we're here. We're going to have small k. Out at this point, for example, the curvature is going to be greater than in these red areas, but it's going to be smaller than where I circled in the black because it's not as tight of a curve. Okay, so the curvature number, and there's a number for curvature. That number is going to vary from 0 up to as big as you want. The greater the curvature, the tighter the curve. Okay, so that's how we define curvature, or that's what we're going to be shooting for. So the question is, how do we find it? Well, it's actually kind of a duh thing. When I put up this for definition of curvature, you're probably going to look at it first and go, wait, what? But if you actually look at it and you think about what the different pieces are, you're going to go, oh, yeah, okay. Now, before we actually get there, though, I have to define one more thing, and that is a different parameter. So before we kind of get to the definition, I'm going to leave a spot for the definition. But I want to give you another parameter, and this is the arc length parameter. So remember what parameter is. It's just a variable that we use to describe the other functions. We've been using t primarily, and that t is time in most contexts. That's why we use little t. And so basically what that's saying is, where are we after a certain amount of time? Okay, so if we plug in t equals 10, that's where we are after 10. Plug in 100, where we are after 100 seconds, 100 time periods, whatever. Now, arc length parameter is kind of the same idea, except now, instead of talking about where we are after a certain amount of time has passed, we're going to be talking about where we are after we've gone a certain distance. So hopefully you see the difference there. So now it's not going to be where are we after 10 seconds have passed. It's going to be where are we after we've traveled 10 meters. Where are we after we've gone 2 light years? Where are we after we've gone 8.6 of your favorite length units? So it's a slightly different perspective, but we should be able to describe any curve in terms of both of them, right? Like if we know everything there is to know about a curve in terms of when we're at those places, we should be able to figure out how far we've gone to get to all those places. And that's what this parameter is going to do. So the parameter that we use for this is S. So instead of t for time, we're going to use S for our arc length. And so it really is, it's a distance traveled. So let me give you an example with a function that you know well, because we're going to be able to describe it pretty easily using arc length. So let's go to this one. We'll go 2D. All right, so you guys all as well. What shape is that?
Circle.
That's our unit circle, centimeter radius 1. All right. Basically, T is our angle, but we can think of it as a time period. But for example, a specific case, let's say that we're right here, which corresponds to T equals pi over 4. I'm going to change this real quick. Actually, I apologize. Put a 2 in front of all you guys. Oh, that doesn't matter. Never mind. Oh, yeah, that'll work. That's good. Okay, so let's go with that. So this isn't a unit, so this is a circle of radius 2. So at pi over 4, we're at this spot. Now, if we're going to use the arc length parameter, we need to know this distance. Because that distance S, there's some trouble with audio.
Yeah, it gets choppy.
All right. Yeah, Victor, I think you're right. It probably is my Bluetooth. Let me, I'm going to pause the recording for a second. We're going to try something. All right. So again, the arc length is going to be the distance that we've traveled. So you may remember from your days in pre-calc and trig that there's a relationship between the angle and the arc length, and that's the good old S equals R theta. But in this case, theta is T. And so we have this formula, S is equal to RT. Since this circle is radius 2, this tells me that S is equal to 2T. So in this specific example, we've gone a distance of pi over 2. So even though the angle was pi over 4, the time that's elapsed is pi over 4, the distance that we've actually traveled is pi over 2. So that's what the arc length parameter is. It's a measure of how far we've gone instead of how long we've been going. And in fact, we could rewrite this. We could rewrite this function as a function, instead of a function of t, it could be a function of s. So we'd have r of s equals 2 cosine of s over 2 to sine of s over 2. Let me rewrite that down here. Just recognize the glare is a little bit gnarly. And where that's coming from, I literally took this equation, s equals 2t. I solved it for t to get s over 2. And then I just replace that s over 2 in for t. So both of these functions, whether I've got it written in terms of the parameter t or in terms of the parameter s, those are both equivalent. Those are both going to map out this circle. It's just this top one is looking at where are we at a given time, and the bottom is where are we after we've gone a certain distance. All right, so does that kind of make sense, this whole arc length parameter idea?
Yeah.
Yeah, we're all good. So in terms of how we find it, it's going to depend upon what our function is. For a circle, it's pretty easy because we've got just good old s equals r theta. So let me show you how we could actually find it otherwise. So we'll come back to curvature. I just need the space. So let's go back to arc length of parametric functions. You guys remember how to do that? That's a legit question. Or how about just arc length in general?
That was like a square root of derivatives, right?
Okay, yep, good. It is a square root of derivatives. And for parametric specifically, it was an integral from, say, a to b So those are some time periods, right? And then we'd have the square root of f prime squared plus g prime squared plus h prime squared. So the arc length itself is just the square root of all the squares. But then we would integrate from a to b to get our specific length. So that kind of ring a bell? I hope a little bit. So here's how we actually figure out what s is as a function of t. So s of t, it's going to be the integral from a to t. So a is just going to be wherever we start. It might be 0. It usually is 0. But we have to choose to start somewhere. And then t is when we're going to end. But we're going to leave that variable so that we'll know how far we've traveled given a certain amount of time that's elapsed. And then in here goes the square root of f prime of u, I'll explain that u in a second, squared, plus g prime of u squared, plus h prime of u squared du. So u is what we call a dummy variable. We just put it there because we know we need something, right? We need an integral, a variable of integration, but we don't want it to be t, because t is reserved for where we're ending. Okay, so that's going to be where we end up. So that's why we put in that u, but otherwise it's got exactly the same structure. And this is how we can actually find s. So let me show you. We'll actually do the circle, because I want you to see that what we did for that circle specifically is just an example of this. So remember, here was our r. So let's get our s, and we'll go from 0 to wherever, because we were kind of defining it at starting at an angle of 0, right, at the positive x-axis. So here's how that would work out. Oh yeah, go ahead.
Are we going to get out constants or vectors?
This is going to end up being a function of t, and this is just going to be a scalar number, because
Okay.
what we're finding is a distance traveled.
Mm-hmm.
It's a distance traveled as we're following along a vector valued function.
Okay.
Okay, so what this is going to actually end up giving us is the relationship between s and t, the relationship between the arc length and the amount of time that's passed. And then we can use that to change our parameterization to being in terms of s. Does that
Okay.
make sense?
Yeah.
So what we should end up with when we do this problem, we should end up with s is equal to 2t. Because that's what we saw with this specific function. Right, the s equals r theta kind of deal for circles. So let's see how that plays out here. So first things first, notice that there is no h. We're only in 2 dimensions, so we can eliminate that. So let's get our derivatives. So we're going to have s of t is an integral from 0 to t, the square root of minus 2 sine of u squared plus 2 cosine of u squared du. So I just changed all the t's to u's so they match my dummy variable. All right, So let's see what happens here. When I square, they both turn positive. So we get a positive 4 sine squared u plus 4 cosine squared u. Well, 4 sine squared plus 4 cosine squared is 4. The square root of 4 is 2. So this is the integral of 0 to t of 2. So 2 du becomes 2u. That I'm going to evaluate at 0 and t. And so the arc length is a function of t. Right? It is a function of t, but it's 2 times t. So we end up with s is equal to 2 times t. And I know for this one, you're probably going, well, sure, but we already knew that. We already knew that with a circle, s is equal to r theta. But this was nice. This was a circle. And if we're not on a circle, we still need to be able to do this. Because if we can get it in terms of the arc length parameter, it can make things a lot easier. All right, so let's do this. Let's change it up just a little bit. I was going to do a helix and in a third, but that makes it kind of not all that different. Here's what we'll do. Let's try another one here where we go with R. It's like a helix, but it's not exact. It's like a stretched out helix. Let's go with R is given by cosine t, sine t, t squared. So in the x and the y, we're just doing circles. And in the z, we're going out with t squared. So we're coming out, but we're stretching out as we go. Let's find the arc length parameter for this. So s of t, not a vector, the integral from 0 to t of the square root minus sine of u squared plus cosine u squared plus 2u squared d. Right, so I'm just using this exact form, just with my different pieces. So we're going to get the integral from 0 to t of 1 plus 4u squared so now we got to integrate that. All right, so what's the integral of 1 plus 4u squared?
Negative 1/2. Never mind. Never mind. Never mind.
Not negative 1/2. How would you do it if you had to do it by hand? And hold on, let me see what you put there in the chat. So Victor says u plus. Right, so 4u cubed over 3. That's what we would get if we didn't have the square root. Be really glad I'm not going to make you do this by hand.
I think we get 2/3 times 1 plus 4u squared to the 3/2 times 4u cubed divided by 3.
All right, say that again.
I think, anyway. 2/3
or 2/3
times 1 plus 4u squared to the 3/2
Okay.
times 4u cubed divided by 3. I think.
How'd you come up with that?
I don't know. Reverse chain rule, I guess.
Okay. So you're trying to do a reverse chain rule. I appreciate that, but unfortunately, that's not going to quite work.
Okay.
All right. If you had to do this by hand, this is trig sub,
Damn it.
right? Where you got a squared plus bx squared, basically. And so when you got the sum of squares, that's where you want to substitute in a tangent. So you would let tangent of theta equal 2u kind of do its thing. But we're going to cheat a little bit. I'm just going to go to Desmos real quick and integrate this thing, because I don't have it off the top of my head.
Bruce, are you expecting us to like go back and refresh ourselves on those methods of integration, or will it for the most part not be like these difficult ones with the fancy substitutions and whatnot?
Okay, so I think really the question is, which integrals do I expect you to know how to do by hand?
Yes.
Okay. The answer is I don't expect any of them. I full on expect that you guys are going to use your calculators or some online resource to do the integration. So that's what I full on expect to have happen. But I will always mention what steps you would have to take to do them by hand. But in reality, no, I don't expect that you know how to do these.
All right, sounds good.
Okay, so here's where we are. Thanks for giving me enough time for Desmos to do its thing. So we get 1/4 times 2u times the square root of 4u squared minus 1 minus the, or sorry, not minus, plus the natural log of 2u plus the square root of, oh, that's a plus on that one, by the way, 4u squared plus 1. Square root of 4u squared plus 1 that we're now evaluating at 0 and t. So obviously, right? You guys all saw that one?
Totally.
Yeah, I figured. I think I need another bracket. So, but from trig sub, that's what you would get, right? You do the letting tangent of theta equal 2u, blah, blah, blah. This turns into integrating secant squared, like secant squared times secant or something like that, and then go. But let's go ahead and evaluate this at t and at 0. So obviously the t just means we replace all these things with t. So we get 1/4 2t square roots of 4t squared plus 1 plus the natural log of 2t plus the square root of 4t squared plus 1. And then we would plug in our 0. Well, when u is 0, this thing goes away. This one becomes natural log of 1, which is also 0. So we're actually done. So this is the arc length parameter for this stretched out helix. So basically, this is what this formula does for us. Think of it as, you tell me how long we've been going, I'll tell you how far we have gone. Right? You give me a time elapse, how much time has elapsed, I'll tell you how much our odometer has changed. How long the path, how long we've been hiking, what distance we've hiked, whatever, however you want to think about it. But this is giving us a distance given an amount of time. Now, this one, if I said, well, let's replace this parameter into this function, would kind of suck. Because we'd have to solve this for t. And I don't know about you, but
Oh.
prospect of that, right? Getting t equals with this is going to be pretty gnarly. So we're not going to do that. Any of that you get on homework where it says change this so that it's in terms of the arc length parameter, this expression should be a lot easier to solve for t. It won't necessarily be as easy as the circle was, right? The circle was really easy. We just had to divide by 2. But you can imagine that, like, let's say that natural log piece was gone. This might not be that terrible to solve for t, right? It sort of just depends. But this also goes to show you how just one little tweak, just putting in that 3-dimensional t squared, made this arc length formula, this arc length parameter, much more complicated, much more gnarly. All right. Well, anyway, that's what the arc length parameter is. It's now just giving us in terms of, it's giving us where we are in terms of how far we've gone instead of how long we've been going. So it's just a slightly different viewpoint. All right, well, with that, now you're probably going, okay, what does this have to do with curvature? Right? You may remember that I started this whole all out as, hey, we're going to see how curvy curves really are. Well, the way that we define curvature, like I said, it makes sense once you kind of look at it. So let me give you that definition, but it involves arc length. So that's why we had to do this first, okay? So we define curvature as k equals the magnitude of d big T ds. So I want you just to look at that for a second. First of all, just bask in its glory. Let its radiance shine upon you. Okay, I know it doesn't really look that impressive, but let's think about what it's actually saying. So we've got magnitudes because we've got a vector in here, right? We've got our t, big T. That is a vector. So we're looking at that. So we're going to be looking at magnitude. This makes it so that it's never negative. You can't have negative curvature. You can only have 0 and greater. Okay, so that's what this is doing. It's just the magnitude. But what we're looking at is how the tangent vector, how that unit tangent vector is changing with respect to arc length or respect to location. So let's think about this. Let's do a couple of different ones where t is changing. So let's say we're starting here with a t that does this, just for the sake of having something, okay? And then it's going to change to this. Okay, so we're going to start with a unit tangent vector that looks like this, and we're going to end with one that looks like that. But we're going to do two different cases. The first one is going to be when our arc length, or a change in arc length, is 1. And the other one is going to be when our change in arc length, let's say, is 4. So what this is saying is that we need to get from a tangent vector that's pointing kind of in this 45-degree or pi over 4 direction to one that's pointing straight right through the process of going over a curve that's length 1. The other one is we're going to do that over a curve that's length 4. So think about what this curve has to do. It has to start going upward, right? And then it's going to have to end parallel. So, or parallel to the x-axis. So maybe if this is length 1, there you go. We went from that t to that t. So let's say that this is length 1. Now on my other curve, I'm going to do that, but over a length of 4. Oh, that's not even 4 times as long. But let's just go with that. So again, we have that same change in our t, but it's over a much longer arc length. So the way that we kind of think about curvature, which of these is a smaller curvature? Which one is straighter? The first one or the second one?
The second one, I would say.
Yeah, the second one. Imagine that this is a mountain road. Right? If this curvature were to continue, let's just kind of continue that curvature. It's going to look like that. This other one, if we kind of continue this curvature, it's going to look like this. This first one, you got people sliding to the side of the door. Right? This is the fun one when you're in the back seat with your siblings and you're playing corners and whatnot. But you have to slow down. This other one, it's a nice gentle curve. You barely even notice it. No big deal. Well, see how this definition works. If we're taking this change and we're dividing by the distance that we've gone, we get the same change over a longer distance. This number is smaller. If we get no change, this number is 0. Think about what that means. No change means that your tangent vector, so here's the tangent vector, no change, I just keep getting the same tangent vector, AKA I'm in a line. So that's what I was saying about how this definition actually really makes sense if you think about it. If t isn't changing much as we're going along, we have a low curvature, and it's not very curvy. If t is changing a lot, then it's got great curvature, and we're very curvy. So kind of go back to that one that I did at the beginning. I don't know that I can actually replicate it, but let's at least do this part. And again, look at what happens with t. So I'm just going to model t with my pen. So here's t as we're going, and so it is changing at a certain rate, and that's that curvature. But if we think about this hairpin curve, that t changes much faster. Like think about how long it takes to go through a quarter rotation. So if I start here, we're at a quarter rotation about there, which wasn't very far, right? It was from here to like there to get 1/4 of a rotation. Come over in this direction. To get 1/4 of a rotation, starting here, I have to go until about there. So this distance was how far it took to do a quarter rotation in my t vector, as opposed to this distance on that sharper turn. So smaller ds means bigger curvature. All right, so basically what this is saying is that if we've got our unit tangent vector in terms of s, we're good to go. We just differentiate it and find its magnitude, and we're done. So go back to that circle. When we did that circle, the first one that we did, we had r of t was just 2 cosine t, 2 sine t. When we converted it to s, s was now 2 cosine of s over 2. R was 2 cosine s over 2, 2 sine of s over 2. And let me show you how we would get the curvature then. So we need big T. All right, well, we know how to find big T. It's the derivative divided by its magnitude, right? So even if we come back to this one, to R prime was minus 2 sine t, 2 cosine t. Its magnitude was the square root of 4 sine squared plus 4 cosine squared, which was 2. So big T was just R prime divided by the magnitude, which is minus sine t cosine t. Convert that to S's. This is minus sine of S over 2 cosine of S over 2. And believe it or not, you probably do believe it, if we had just found R prime of S here, we get exactly the same thing when we divide by its magnitude. Let me actually show you real fast. So R prime with respect to S is going to be minus sine of S over 2, because the 1/2 comes out from the chain rule, and then cosine of S over 2. The magnitude of this, square root of sine squared S over 2 plus cosine squared S over 2. Well, sine squared plus cosine squared is 1, square root of 1 is 1. So dividing by the magnitude is itself. And notice that these two are equivalent. So we don't even have to bother doing all of this stuff with T if it's already in terms of S. You can actually get your T of S the same way we did before. But now let's find our curvature. So we'll go back to the definition. The curvature, it is the derivative of this with respect to S, and then take its magnitude. So it's going to be the magnitude of minus 1/2 cosine of S over 2, comma, minus 1/2 sine of S over 2. And now we need its magnitude. So it's going to be the square root of 1/4 cosine squared S over 2 plus 1/4 sine squared S over 2. So that's the square root of 1/4, which is 1/2. So what we just found out is that the curvature of that circle is 1/2. It's also not dependent on T, which means that the curvature of the circle is the same everywhere. But that should make sense, right? Circles are nice and regular. The curve of it is the same in all spots. So it should be good. It should be the same everywhere. And in this case, it is 1/2.
Bruce, could you repeat how you got the vector negative 1/2 cosine of S over 2, negative 1/2 sine of S over 2?
This part right here?
Yeah. Where did you
Okay.
get that?
So I went to right here, because that's my T, and I differentiated it with respect to S.
Gotcha.
All right, cool? Now, I want you to think about this though. This definition requires that we have this thing in terms of S. We have this in terms of the arc length parameter. And that's not always the case, right? And in fact, we saw that trying to change it from T to S could be kind of a pain. Like, look at what happened with that weird Helix thing. We got that horrible formula that related S and T. So having it this way isn't optimal. Like, yes, it's a great definition, but it's horrible for actually like working out and doing things with it. So let me give you some other ways that we can define curvature that bring it back to other forms that are much more likely for us to have. Okay, and specifically, let's start with if we're in terms of T.
Bruce, can I ask you another quick question?
Absolutely.
What did you plug into S after you took the derivative of
I
T?
didn't.
You didn't plug anything in?
Nope. No, I just took it as the functions, and the reason they all went away is because I had a sine squared plus cosine squared,
I see.
and that always equals 1.
Gotcha.
So in general, there are going to be S's left over. So you'll get curvature that is a function of S, because the curvature is going to depend on where you are. It just worked out that in this case it didn't, because it was a circle, and curvature is always the same with a circle. So is that good?
That's great.
Okay. So I'm going to give you a couple more formulas, but this next one we're actually going to develop it, but we're going to build it using this definition. So think about what we're doing. We're doing a dt ds, and we're getting it in terms of its magnitude. But what we do know from the chain rule is that dt ds is going to equal dt d little t times dt ds. So hopefully you kind of remember the chain rule stuff. So we get here. So what we can do is actually rewrite this as dt dt over ds dt. So think about this magnitude then. This is going to equal, let me just kind of put a little squiggly here to designate what I'm doing. So I'm working on this guy. I'm going to replace it with the magnitude of dt dt divided by the magnitude of ds dt. So literally, I'm just replacing this. Right, I'm just firing that in there. Okay, so this is getting good. It's getting back in terms of t, but we need to get rid of that ds dt, specifically its magnitude. So I want you to go back and think about how we defined S, right? S was the square, well, it was the integral from a to t of that square root of f prime squared plus g prime squared plus h prime squared, right? So what we're doing is we're going to take this and we're going to differentiate it with respect to t. So what happens when you differentiate an integral?
You get the function.
Yeah, you just get the function. You get what we started with. So this magnitude, well, so the ds dt is just going to be the square root of f prime squared plus g prime squared plus h prime squared. Well, I don't know if you recognize that, but that's also known as the magnitude of r prime. So what we're doing is we're taking the magnitude of r prime, which is really just the magnitude of r prime. So here's a second form then for curvature. We can think of curvature as the magnitude of dt dt divided by the magnitude of r prime of t. So I'm just going to put these in separate boxes to draw your attention to them. But these are equivalent. They are exactly the same thing. But this second one is a little bit nicer in terms of functionality because we don't have to find the arc length parameter. We can do this just in terms of t. Okay, so all of this just was how we developed this formula. So let me show you this formula with that helix-ish thing where we saw the conversion between arc length and t was really kind of ugly and nasty, and how we can use this to get around it. So let's go back to that guy where we had r was cosine sine t squared. So what we need to do is we need to find the unit tangent vector so that then we can differentiate it. We need to find r prime so we get its magnitude. So let's get r prime. R prime is negative sine cosine 2t. Before I find big T, let's get the magnitude of this. We actually already found that earlier, but it's the square root of 1 plus 4t squared. So there's our r prime. So that's what's going to go on the bottom. But now let's get our t. So big T is minus sine of t over square root of 1 plus 4t squared. Cosine of t over square root of 1 plus 4t squared. 2t over square root of 1 plus 4t squared. All right, so now we need to differentiate big T. So this is going to require some quotient rule. So we're going to get minus cosine t times the square root of 1 plus 4t squared minus a negative sine t times 1/2 1 plus 4t squared to the minus 1/2 times 8t all over 1 plus 4t squared. This is just the x component of dt dt. The y component is going to be similar, minus sine times this stuff, minus cosine times 1/2 times 1 plus 4t squared to the minus 1/2 times 8t. And then the z component, no sines or cosines anymore. So I'll give you a minute to kind of catch up with that. But that's all quotient rule. 3 rounds of it, 1 for each of the components. So now we're going to get our curvature by taking the magnitude of this and dividing by the magnitude of r prime. I think at this point I'm going to spare you. I'm not going to find the magnitude of that. But it's just the square root of the squares of all these added together. I'm sure it simplifies. I'm sure it's going to simplify a lot because we're going to get cosine squareds and sine squareds, square roots that are being squared, right? Things are going to simplify a lot. But then we take that magnitude and divide by the square root of 1 plus 4t squared. So yes, there is more to do, but at this point, I'm just going to go, this is ugly, but doable. We can do it. We can get the curvature of this thing. It's not going to be pretty, but we can do it and we can get it. And it's going to be in terms of t, which now means if all we know where it is at a certain point in time, kind of like was given to us at the beginning, we've got that formula. We don't have to substitute back in. And if you think that this is so ugly and horrible and you're like, well, fine, screw it, I don't want to do it, let's just go back to the definition. Remember what that definition required. It required writing this function in terms of the arc length parameter, which may not have even been doable. I don't know that that formula we found involving s and t for this curve can actually be solved for t. And in math, we're all about, can we do it? Can we get to a form that works? So here's an alternative form that doesn't require us to find that arc length parameter. Now, it still sucks because we still have to find big T and all that. But it turns out that there's yet another way of doing this. So I'm going to put an or. This one I'm not going to prove. I'll let you either read the proof on your own or come find me in an office hour and I will walk it through for you. But what this looks like is it's the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. So again, another formula.
Do you recommend that we know that last formula?
Say again?
Do you recommend that we know that last formula?
Yeah. This is really useful. Because let me show you with this example. Remember how we were going, everything was great, and then we had to find the magnitude of this big derivative, and that's when we kind of went, well, screw it. Let me show you how this other one is a little bit easier. So let me come back over here. I'm going to erase from t on down because this stuff doesn't matter for this third form. But look at what this one requires. It requires us knowing both the derivative and the second derivative. So we've already got the derivative. Let's get the second derivative. It's going to be minus cosine minus sine 2. And then we need to get r prime crossed r double prime. Now, not only is this doable, it's going to be a little bit faster So in terms of components, we're going to get 2 cosine minus a negative 2t sine, so plus 2t sine. That's our I component. Our j component is going to be minus 2 cosine plus 2 sine. And our k component is going to be sine squared plus cosine squared, which is 1. So this is r prime crossed r double prime. So now we need its magnitude. Okay, well that's just the square root of all of this. Okay, so there's the magnitude of r prime cross r double prime. So then to get our curvature, the curvature is just this divided by the square root of 1 plus 4t squared cubed. That was the magnitude of r prime cubed. So remember that big horrible thing that we were in the process of when I finally said, yeah, this is ugly, I don't want to go any further? Had we kept going, had we simplified, it eventually would have turned into this. So this third form is by far the preferred form for space curves. Because in general, you're going to be given r prime, or I mean r. You're going to know r, so you can find r prime and r double prime pretty quickly. The cross product is what it is, but then you just take magnitudes and you're good to go. So think about the calculus involved. The calculus is small. It's 2 steps of finding derivatives at the very beginning. After that, it's just algebra. This is vector algebra. So I forget who it was that asked me if I recommend memorizing this. I think it may have been you, Seamus. If not, it was whomever. But yeah, I definitely suggest you remember this one, because this one is the most useful for space curves. All right, there is one more formula for curves in the plane, but we're going to do that next time. I'm actually going to stop here because I don't really have enough time to develop the one for curves that are in the XY plane. But that one we're going to want for when we have just regular old nice functions and stuff like that. So I'll show that to you on Wednesday. Okay, so just a couple things to remind you about. First homework sets are due tonight at midnight. So you got a couple sections to work on, make sure that those are in. And then also our first quiz is coming up on Friday. We'll talk more about that on Wednesday. Okay. So with that, are there any last questions before we move on, before we call it a day? So I know that this is a lot to digest, okay, but the most important thing is just to remember the definition of curvature, where it really comes from, and think about what curvature means, because that's what we're going to use going forward. All right, well, with that, I'm going to go ahead and stop our recording and wish you all a great couple of days, and I'll see you on Wednesday.
So did you say